Assalamu alaikum. This is chemistry 12th, and our today's topic is the properties of these haloarenes. Dear students, as we have already discussed the synthesis of these haloarenes, we have discussed various methods. For example, we have discussed the direct halogenation of these benzene in presence of some halogen carrier, like we have got this perichloride, we have got aluminum chloride. Then we discussed the Sandmeyer's reaction, which is a well-known reaction that is used for the synthesis of these haloarenes. Similarly, we discussed the that Gattermann's reaction. So they have those were the methods for the synthesis of these haloarenes. Now, as far as the properties of these haloarenes are concerned, we have got two types of properties, as you know, physical properties, and we have got chemical properties. Now, as far as the physical properties are concerned, these include the physical state. First of all, we'll see the physical state of these aryl halides. Now, as far as the physical state of these aryl halides is concerned, these are colorless oily liquids, or they can be crystalline or crystalline solids. Then we have the solubility. Now, as far as the solubility of these aryl halides is concerned, these are insoluble in water, acids and bases, but they are readily soluble in case of these in organic solvents. Then we have got the boiling points. Now, as far as the boiling points of these haloarenes are concerned, the boiling points of monohalogen derivatives of benzene, they follow this order, that is iodobenzene, it is boiling point is greater than bromobenzene, and then which is still greater than that chlorobenzene. Now, as far as these dihalogen derivatives of benzene are concerned, now in case of isomeric dihalogen derivatives, we see 1 2, we have got 1 2 dichloro, this is benzene. Then we have got 1 3 dichlorobenzene. Then we have got 1 4 dichlorobenzene. Now, their boiling points are the boiling points of these isomeric dihalogen derivatives of benzene are concerned, they are nearly same. For example, we see the boiling point of this ortho isomer, that is ortho dichlorobenzene, it is 453 Kelvin. Then we see the meta isomer, that is 1 3 dichlorobenzene, it is 446 Kelvin. Then we have got para isomer, that is 1 4 dichlorobenzene, it is 448 Kelvin. Now these are the boiling points which are nearly same. Now, as far as the melting points are concerned, the melting points of these isomeric dihalides, they are quite different. For example, the melting point of this para isomer, that is 1 4 dichlorobenzene, it is 70 to 100 degree greater than the other two isomers, that is ortho and meta dichlorobenzene. Now, you see the melting point of this ortho isomer, it is 256. Then we see the melting point of this meta dichlorobenzene, it is 249. Then we see the melting point of this 1 4 di, that is para, it is 325 Kelvin. Now the high melting point of this para isomer, it is because of its symmetry. That means it has got a symmetrical nature. Now, this because of its symmetry, this leads to close packing of its molecules in the crystal lattice, and obviously the melting point gets increased. Now, then we have got the density. Now, as far as the density of these aryl halides or haloarenes is concerned, now these aryl halides, they are heavier than water. However, the density follows the order, that is iodobenzene, they have got high density, then bromobenzene which has got high density than chlorobenzene. Now, these are the various these physical properties of these haloarenes. Then we have got the chemical properties. As far as the chemical properties of these haloarenes are concerned, these haloarenes, they are very much less reactive towards the nucleophilic substitution reactions as compared to the haloalkanes. Now, the less reactivity of these haloarenes towards these nucleophilic substitution reactions can be explained as the phenyl ring in these haloarenes, it acts as an electron withdrawing group. it acts as an electron withdrawing group. The lone pair of electrons on the halogen atom, it is in conjugation with the pi electrons of this aromatic ring, giving rise to various canonical structures or resonance structures. This is known as resonance, and these are the various canonical structures. You see how this lone pair, it is in conjugation with this gets shifted, the negative charge moves to this, then it goes to this and goes to this position. So these are the various canonical structures. Look if we closely look at these canonical structures, we see here the structures. This is 2, 3, and 4. The C, now looking at these three structures, that is 2, 3, and 4, we see that the CX bond, in case of these haloarenes, it has got a partial double bond character. Now because of its partial double bond character, this CX bond, it becomes shorter and stronger. Now as a result of which its cleavage becomes very difficult. So this is why these aryl halides, they are less reactive towards these nucleophilic substitution reactions as compared to alkyl halides. Now the reason is that the CX bond is shorter and stronger as compared to the CX bond in case of, as we saw in case of these haloalkanes. There it is not as strong as it is in case of aryl halides. Now these aryl halides, they can undergo these do not undergo these nucleophilic substitution reactions easily. However, they can undergo nucleophilic reactions under special conditions. That means under specific conditions. Now some of the nucleophilic reactions in case of these haloarenes are, we have got this reaction with sodium hydroxide. Now aryl halides on treatment with this aqueous solution of sodium hydroxide, they give rise to the formation of the phenol. Now you see here how chlorobenzene, it reacts with aqueous solution of this sodium hydroxide at a temperature of 623 Kelvin and at a pressure of 200 to 300 atmospheres to give rise to the formation of phenol. So it takes place under these specific conditions, that is temperature is to be maintained at 623 and the pressure is to be also maintained at this 200 to 300 atmospheres. Then we have got the other this nucleophilic substitution reaction, that is the reaction with ammonia. And now this is also known as ammonolysis. Now in this reaction, when these aryl halides are treated with ammonia in presence of this cuprous oxide at a temperature of this 473 Kelvin and at a pressure of 60 atmospheres, the product formed is aniline. Now plus cuprous chloride and water. Again we see here that the temperature is to be maintained at 473 Kelvin and pressure is to be maintained at 60 atmospheres. Then we have got the reaction with cuprous cyanide. Now in this reaction we see that this bromine atom here, in case of bromobenzene, it gets replaced by this cyano group. Now when bromobenzene, it is treated with cuprous cyanide at a temperature of 470 to 75 Kelvin in presence of a base, that is pyridine, we get a cyanobenzene, or we can call it as benzene nitrile or benzonitrile plus cuprous bromide. Now then we have got the reaction with metals. Now as far as the metals are concerned, the reaction with magnesium, so this is again a well-known reaction. In this reaction, aryl halides are treated with magnesium in presence of dry ether. In presence of dry ether, they give rise to the formation of phenyl magnesium halide. Now you see here in this reaction, we see that chlorobenzene, it is not suited for this reaction. Instead, this bromobenzene, when it is treated with magnesium in presence of dry ether, we get phenyl magnesium bromide. This is also known as Grignard's reagent. So this is how aryl halides react with magnesium in presence of dry ether. Then we have got the reaction with sodium metal. Now in this case, we see that when an aryl halide molecule plus an alkyl halide molecule, it reacts with metallic sodium in presence of dry ether. In presence of dry ether, the product formed will be toluene plus NaCl. Now in this reaction, we see, since we use two different molecules, we use an an alkyl halide plus an aryl halide molecule. So this reaction is known as Wertz-Fittig reaction. But in case of alkyl halides, where we saw that when two alkyl halide molecules react with metallic sodium, they give rise to the formation of a higher alkane. There we simply call it as Wertz reaction. But here, since we use two different, we use an alkyl halide plus aryl halide molecule, and the product is toluene. So this reaction is called as this. What is Fittig reaction? Now, instead of this alkyl halide molecule, that is methyl chloride, if we use two similar aryl halide molecules, then again using this metallic sodium, we see here, and when chlorobenzene, it is two molecules of chlorobenzene, they react with metallic sodium, they give rise to the entrance of dry ether, and they give rise to the formation of this is diphenyl plus NaCl. Now this is what is reaction, what is Fittig reaction. Then we have got the reaction with Q plus then we have got the reaction with copper powder. Now the condensation of these two aryl halide molecules, it can be also brought about by using this copper powder instead of this metallic sodium. Now this reaction takes place at a high temperature, and in this reaction we see iodoarenes are particularly, they are suited for this reaction. You see here, this iodobenzene, when it is treated with copper powder, that means two iodoarenes are treated with copper powder at a high temperature, they give rise to the formation of this diphenyl plus Q plus iodide. So this reaction is known as, it is also known as Ullmann's reaction. Now you see here, the condensation can be brought about by using copper powder. In case in place of, we can use and this in place of we can use instead of this sodium, we can use copper powder. This is in Ullmann's reaction. Then we have got reduction. Now as far as the reduction of these haloarenes is concerned, we can use different types of reducing agents. Now you see here, we can use here nickel aluminum alloy in alkali. Now you see here chlorobenzene, when it is reduced using this nickel aluminum alloy in an alkali, that is sodium hydroxide, the product will be this chlorobenzene. It is reduced to benzene plus HCl. So these are the various reactions of these aryl halides. Then we have got the electrophilic substitution reactions are concerned. Now as far as the these substitution reactions are concerned, we will discuss it in our next lecture. This is for today. Thank you very much.